talking about aqueous solutions, whenever we use the word aqueous, we're talking about solutions that are in water, so water-based solutions. So anytime you see aqueous, or for example, if I've got like sodium chloride, NaCl here, and I put the subscript AQ next to it, that means that I've dissolved that salt into water. So in reality, this means NH2O. Okay? So it's just a water-based solution. When we have any sort of material dissolved in a solvent, we've got to define those terms. So since water is the universal solvent, we'll use this as an example. So anything that dissolves in a solution is going to be called a solute. All right? Anything that dissolves the solute is going to be a solution. So that which contains the solute is going to be considered a solution. Okay? So for right now, I'm just going to talk about this in terms of water. All right? And to do that, I have to first talk about water itself. Now, water is a special little molecule. H2O, as we've seen in our VESPR videos, now water is a bent shape. And because of that, water, the OH bonds, have two dipoles that are not canceling each other out. So the dipoles of both of these are pointing towards that oxygen, which means that the molecule itself has an overall dipole moment. And that dipole moment is going to induce a certain amount of polarity that's in the system. In addition to that, there's an intermolecular force called hydrogen bonding. What this means is that when I have water, because the electrons are flowing towards that oxygen, the oxygen is considered to have a partial negative charge, and that's a little d, a little delta, right? So it's got a partial negative charge, not a full negative charge. But down here in the hydrogens, I've got a partial positive charge, because the oxygen's electronegativity is sucking those electrons away from the hydrogens and making them positive. So anytime I have water, and I know it's proven that it's going to be a polar molecule, any other water that's nearby is also polar, and we get an interaction between these two. And because this is partially positive, and this is partially negative, excuse me, partially negative up here, partially positive, partially negative, partially positive, the positive and the negative are going to stick together. This is called a dipole-dipole interaction. Okay, so it's a dipole-dipole intermolecular, which means between molecules, interaction. The intermolecular reaction that we get, the stickiness, isn't strong. It doesn't have the full energy of a bond, but it does have a certain amount of energy, a strong amount of energy. And that energy that's bound inside of there is especially magnified between these hydrogens and this oxygen. And that magnification is something that we're going to call hydrogen bonding. Okay? And because of that hydrogen bonding between the water molecules, this is why water only weighs 18 but boils at 100, is because you have to overcome all of this really stickiness that's going on there. Okay? So this is called a polar molecule. All right? So we can consider these molecules to be polar. Okay? Now I have to describe it in terms of what's happening in the solution, so make this all disappear. All right. Here I've got three water molecules, and I've got this kind of negative cavity that I've developed because I put oxygens around there. And if I have something that is an ionic system, okay, so I'm dealing with ionic systems right now, something like sodium chloride, this is going to have a certain effect. Now, as you guys know, sodium chloride is an ionic salt, and as an ionic system, I've got a positively charged sodium stuck to a negatively charged chlorine. So when I look at this, the sodium, because it's got a positive charge, is going to be stuck to those oxygens. Those oxygens, being polar, stick to the sodium and help sort of loosen that atom and break it apart from the chlorine. Now the chlorine is also assisted because it's going to have other water molecules nearby, but pointing in the opposite direction, solvating it. Oh, there we go. No dotted lines just yet. Okay. So because those hydrogens are nearby, they're going to be able to grab that chlorine. It's going to be able to pull this ionic, this polar system apart. All right? That's why salts dissolve in water so readily, is that the water is able to stabilize the ions in the solo form. So the ions are able to float apart from themselves inside of these solutions. Okay? Now when I have anything that I put into water and it dissolves immediately, okay, it's going to be called a strong electrolyte. To use nerdy terms, a strong electrolyte is going to completely dissolve when it hits water, okay, up to the point where water is saturated. So this completely dissolves. In the solvent, okay? And actually, because we're talking about electrolytes, we're going to be talking about in water, okay? Now, one thing you should know about these electrolytes, okay, is that when they're strong, generally they're also going to increase the conductivity of water. If you think about salt water versus regular water, water itself is just floating around as H2O molecules. But once I put the salt inside of there, I now have a system that's got charged sodiums and charged chlorines, and they're adding to the overall ionic nature of the water. This allows electricity to flow through water a little bit easier. Okay, so this increases conductivity of water. Okay, if I have a weak electrolyte, you can probably guess where we're going with this, right? A weak electrolyte is not going to completely dissolve in water. Okay, and it does increase the conductivity of water. To give you an idea, am I running off the screen here? Let's see. Hope not. Nope, I'm still good. All right. To give you an idea of some examples that are associated with this, right? We've seen sodium chloride. Sodium chloride floats apart into two different ions. If you think about that, so I've got two ions for every one molecule. I'm really going to jazz up the electronic conductivity of water. The same thing happens with strong acids. A strong acid is just like a strong electrolyte, where it's going to dissolve completely in water. So if you think about a strong acid, HCl, okay, I put that into water, it's going to completely dissociate, and I'm actually going to be able to increase the conductivity of water. Okay? If I have a weak acid, like HC2H3O2 or acetic acid, that does not completely dissolve in water, okay? But it does to a certain extent. Because we can taste vinegar, okay, and it's got that sour taste to it, we know that it's an acid. So vinegar itself doesn't dissolve completely in water, but does dissolve to a certain extent in water. And as a result, it will conduct electricity. Okay? There are some examples of videos on the old YouTubes where people are using different salts, okay, different like HCl versus acetic acid, and they're running electricity through them to light up light bulbs. I wish I had a setup like that and I could show that to you, but I don't. So I will lead you to the YouTubes to watch those videos. Okay? Now, I was thinking about this and you thought the video was over, but you were wrong, right? I introduced a concept that I think you guys really need to understand a little bit more, especially going into second semester general chemistry. So I'm going to touch on it right here. And this is a concept called equilibrium. Okay? And we represent equilibrium by having a double-headed arrow. Okay? This means the reaction is going forward and going backwards. Now, when I have something that's a strong electrolyte, it means it's going to produce ions very easily. So what this means is that H3O plus and Cl minus, both of these are aqueous. Okay, water is a liquid. Water can't be aqueous because it dissolves itself at that point, which it does. It makes it a little bit confusing, but we call it a liquid because it's going to be pure. All right. So if I bubble HCl through water, I'm going to get H3O plus and Cl minus. Right? What species exists in the water? That's an important question. Is it HCl or is it H3O plus and Cl minus? Well, after scientific survey, we discovered that when you add HCl to this, HCl is going to dissociate or break into ions of H plus and Cl minus. The H plus is actually absorbed by the water, become H3O plus, called something important, hydronium. Okay? So hydronium itself and chlorine are produced in large quantities when HCl, because HCl is a strong electrolyte. It's going to break into water. So our equilibrium lies strongly with the products and weakly with the reactants. That means that most of the reaction is going to go this way. But sometimes you're going to have the Cl come and grab a hydrogen and go back this way to make HCl. Okay? This equilibrium lies with the products, though. When I have acetic acid, all right, and I react this with water, so if I just drop in solid acetic acid, put this in the water, because this is a weak electrolyte, I don't get much of this stuff, H3O plus and acetate. Okay? So as a result, my equilibrium arrow is going to lie with the reactants. Okay? So I have a little bit going forward, a lot going in that direction. We can study and quantify the magnitude of these values in equilibrium using something called equilibrium equations. Okay? And this is something you study in second semester. It's a very important concept. But all it is just studying which side is going to lie towards the products. Okay? To know this, we're going to use something called an equilibrium constant. There you go. So now you're familiar with it. You've seen this before you hit Gen Chem 2. And the equilibrium product is just equal to the concentration of your products over the concentration of your reactants. Okay? Basic concept. If I have more products than reactants, my K is going to be greater than 1. So at this top form, my K is greater than 1. That means that my equilibrium is lying over here with the products, right? Because I have more products than reactants. If this is 8 and this is 1, what's K equal to? 8. It's greater than 1. Hello? All right, good. Just the opposite. If reactants are large and products are small, my K is less than 1. And when my K is less than 1, that means that my equilibrium is lying with the reactants in favor. Okay? So that's what defines what a strong electrolyte and a weak electrolyte are. You're welcome.